Cool, cool. Well, this will be my first ever live stream on this channel, and I'm excited. I love live streams, and I always say that it's an avenue one to really be able to focus on learning some things, because nowadays it's easy for us to just jump from one place to the other. Like when you're learning on your own, especially when no one else is forcing you to learn, like you're not attending school, so you're not doing it because school is asking you to do it. Sometimes it becomes really challenging for you to learn the things that you want to learn, because you have your phone. Like right now my phone is lying right here, so ordinarily you would be learning, and by then you realize you've reached for your phone and you wouldn't even think about it, but find yourself down that rabbit hole. So my well, one of the reasons why I enjoy doing live streams is because, especially with the study with me streams I used to do back in the day, you would be able to focus and take breaks and have a chat with some of the people who are viewing it. But yeah, on a new channel where no one knows you, that's pretty cool. So let's see. Today I'm learning about classification. So over the past couple of weeks, I've been reviewing my machine learning concept. So if you come across the video, you don't know me in person, maybe I should introduce myself. So Onyao as the name, and I have I professionally trained as a pharmacist. So I have a doctor of pharmacy degree. Then I transitioned into software engineering. Then I transitioned into health informatics. Currently, I'm building a startup, and I'm the CTO of the startup. In fact, it's not building, like the startup is actually live right now. Like people are already using it. We have users who are already using the product. I'm the CTO there. And as part of the work we do at the startup, and maybe sometime later I'll talk about what exactly the startup is, but we have a lot of AI components and some machine learning component. Over the past 3 to 4 months, I taught myself AI engineering. And the thing about it is the product we're building forced me to learn a lot of the things to be able to build. And I enjoy doing it. And I believe that now where we are, as a software engineer, the next level is learning how to consume these AI agents or LLMs and even building your own agent. So it was the next obvious step for me to learn AI engineering and become an AI engineer. But the more I do that, the more I also enjoy the machine learning behind it. Like before they built the model for us to be able to build a system or a software around the model, how exactly did they think about the model and build it? And over several years, I've tried learning machine learning here and there, right? So some of these concepts are not totally new to me. And when I think about it, I realize that this is how I mostly learn almost anything. Like there are times where I just go learn some of them, forget about it, come back later, learn something about them. Then when I really need it, I go hardcore into it, and now I master it. And I think that is really helpful, especially when you learn this without you being required to. So no one is requiring me to learn these things. I just enjoy learning and I'm learning them. And I feel they are really cool. So I came across this Google Developer Machine Learning Crash Course, and I've been using that to revise the concept. So far, I've done the logistic regression one. So I'm currently planning a project around logistic regression, and I want that project to be based on what we do at our startup, so that at the end of the day, the products that I build or the projects that I build would be useful to the users in our platform. So that's what I'm trying to do. And today I want to review classification. The estimated time here is 70 minutes. Let's see how it goes. And let me see, maybe I do this because I like to teach. So maybe let's see, learning by teaching. I always preach that if you want to really understand something, make sure you teach what you learn, right? But that meant that you should have learned the thing before teaching. But now let's take a different approach. I'm going to try learning this thing whilst teaching it. Learning it on the fly as I am teaching it. So we're learning about classification, and essentially the concept of classification is if you can put things into classes. So you are training a machine, you're training a computer to be able to classify things. Let's say if you give it certain things, let's use popular examples. Say you give it images, you want it to classify the image. Is this an image of a dog or a cat? That'd be a classification problem because you just want the machine to be able to identify whether it is this or that. So that's essentially what classification is, being able to put things in a particular class or group. That's the essence of classification. There is a concept of binary classification. Binary means two. So that's when you have only two classes. In fact, there's also the possibility of having multi-class classification. But in this case, if you say binary, so the model that we're going to build would be more so used to classify between two things, between two labels. So it's either this or that. Okay, on the side, I am also working, which is more currently on my startup code, but I'm making Cloud Code do some review of the code. So along the line, I'll be peeping here to see what Cloud Code has done, then reviewing it. Okay, so our learning objectives for today is one, determine an appropriate threshold for a binary classification model. Appropriate threshold. Okay. And to calculate and choose appropriate metrics to evaluate a binary classification. So we're looking at when we are classifying the threshold with which we'll be able to classify between two things or two labels. Then we would also look at how do I calculate and how do I choose the appropriate metrics to evaluate my binary classification model. So after you have created a model, you want to be able to evaluate it to see whether it's working perfectly or any improvement. So we're going to be able to calculate and choose appropriate metrics. Then finally, we learn to understand ROC and AUC. I remember AUC very well because back in pharmacy school, this was nope. Back in pharmacy school, AUC was one of the important things that we used, important metrics that we use when we're thinking about concentration of any drug, like when you want to try and understand the path of the drug in the body. So it's area under the curve. I remember very well. But ROC, I don't remember ROC. I don't know what it is. So hopefully we find it to be able to interpret ROC and AUC, where AUC is area under the curve. The prerequisite here is it assumes that you're familiar with the introduction to machine learning. I'm familiar with it. Linear regression, I'm familiar with it. Then there is logistic regression. I'm familiar with that as well. In the logistic regression module, you learned how to use the sigmoid function. Yes. And that was one of the things that initially I didn't have a good understanding of. But as I went through it, one of the things that really helped me was when I was trying, like in the logistic regression lesson, I was struggling to answer some questions. So I used the Ask Gemini here. So I use that. Then I asked it question. And the good thing is that it has visibility into this. So in this case, for instance, I would say, what does ROC mean? And this has been a game changer for me when I'm learning, especially if I'm learning in a browser like this, because it has the context, so I can easily ask it and understand what it means. So in the context of machine learning classification, ROC stands for receiver operating characteristic. Receiver operating characteristics. So an ROC curve is a graph that shows the performance of a classification model at all possible classification thresholds. A graph that shows the performance of the classification model at all possible classification thresholds. So it maps the relationship between two key metrics: the positive rate, TPR, true positive rate, TPR. Okay, true positive rate. That's how many times it got the positive correct. And false positive rate, that's FPR. So TPR, also known as recall. Interesting. I know I have heard a lot of times about recall, but I didn't know that it is also known as TPR. So true positive rate, also known as recall. This measures the proportion of actual positives that were correctly identified. And false positive rate, this measures the proportion of actual negatives that were incorrectly classified as positives. So false positive rates, the total that were classified as positive, but actually they were not. So that is false positive rate. Then the true positive are the percentage of what was classified as positive, which were actually positive. How this works, the curve is created by plotting the TPR against the FPR as you vary the threshold for assigning an item to a class. So example, changing the cutoff probability from 0.9 to 0.1 to 0.9. The top left corner. A perfect model would reach the top left corner, representing 100% sensitivity, which is no false negatives, and 100% specificity, no false positives. Interesting. Top left corner. 100% sensitivity, 100% specificity. And these two terms, sensitivity and specificity, is also something, these are also terms that I got used to a lot from pharmacy school. Because when you're talking about medications that you give your patients, you have to think about the sensitivity of the drug and the specificity, especially if it is we have concepts known as enzymes or hormones and enzymes. In those topics, usually depending on what medication you're giving to the patient, you need to understand how specific is this and how sensitive it is as well. And even against against bacteria, if you take antibacterial agents, we also used to think about sensitivity and specificity to guide your selection of the antimicrobial agent. The reason some of these things that I'm saying is important when you're learning is because my brain already knows certain things, right? Like the topic of sensitivity, specificity. So by trying to create that association, it really helps for me to understand the new thing and absorb it well, because the old ones are ingrained in the brain. So if I can connect the new thing that I'm learning to something that's already existing in the brain, then it's easy for it to stay or stick. Okay. Then the diagonal line, a diagonal line from the bottom left to the top right represents a model that is no better than random guessing. Okay. All right. You would often see ROC mentioned alongside AUC, and AUC is area under the curve. Yeah, I remember that. AUC, wait, what was ROC? Receiver operating characteristic. Receiver operating characteristic. Receiver operating characteristic. Why is it called that way? Because why is it called receiver operating characteristic? Just by mention of the name, nothing really stands out. Ideally, the name should give off something. Why is it called that way? Receiver operating characteristic. Then we talked under that one, we saw true positive rate and false positive rate. Okay. Then let's go. So you learn how to use the sigmoid function to convert raw model output to a value between 0 and 1 to make probabilistic predictions. Yeah, I remember that. The sigmoid function G of Z was equal to, is that it? Here, 1 over 1 minus e raised to the power minus Z. Okay. To convert raw model value to a value between 0 and 1 to make probabilistic prediction. For example, predicting that a given email has a 75% chance of being spam. But what if your goal is not to output probability, but a category? For example, predicting whether a given email is spam and not spam. So we will use the concept of the logistic regression where we get in the probability, but then we can use that probability and have a certain threshold that says that If this is greater than say 80%, then it is spam. If it is less than that, then it's no spam. Okay, that becomes classification. So classification is the task of predicting which of a set of classes, that's the categories, an example belongs to. In this module, you would learn how to convert a logistic regression model that predicts a probability into a binary classification model that predicts one of two classes. You'd also learn how to choose and calculate appropriate metrics to evaluate the quality of a classification model's predictions. Finally, you'd get a brief introduction to multi-class classification problems, which are discussed in more depth later in the course. Okay, let's go. Thresholds and confusion matrix. I feel like I keep hearing confusion matrix almost every now and then when I think about machine learning, but I can't really recall exactly what a confusion matrix is. I know it's a matrix, of course, but why and when do we use a confusion matrix? So that's definitely something I'm curious about. So let's say you have a logistic regression model for spam email detection that predicts a value between 0 and 1. This representing the probability that a given spam is email. Wait, a given email is spam. Did I just read that? A given email is spam. A prediction of 0.5 signifies a 50% likelihood that the email is spam. A prediction of 0.75 signifies a 75% likelihood that the email is spam, and so on. You'd like to deploy this model in an email application to filter spam into a separate mail folder. But to do so, you need to convert the model's raw numerical output, example 0.75, into one of two categories, spam or not spam. To make this conversion, you choose a threshold probability called a classification threshold. Okay. So basically, from what we've read so far, classification, in fact, I was having a conversation with a friend a couple of days back to try and understand at what point in time would I use linear regression and at what point in time will I use logistic regression. And I remember we reached the conclusion, at least for my understanding, that logistic regression is for classification problems. So yeah, it's for classification problem. And now I understand why, because basically what we've learned about classification so far is that it's still logistic regression that we are doing, except that now we are setting what we would call the classification threshold. And based on that threshold, once we get the output of the logistic regression, which will give us a probability score, we can compare that score against the threshold and be able to now classify the score or classify the value as to which of the classes it belongs to. All right. To make this conversion, you choose a threshold probability called a classification threshold. Examples with a probability above the threshold value are then assigned to the positive class. So examples with a probability above the threshold value are then assigned to the positive class. So we have a positive and a negative class. The positive class is whatever is greater than the classification threshold. And then the other becomes the negative class. Okay. So here the positive class would be that it is a spam, and the negative class would be that it is not a spam. She may be wondering what happens if the predicted score is equal. Yeah, I'm actually wondering. To the classification threshold. For instance, a score of 0.5 where the classification threshold is also 0.5. Handling for this case depends on the particular implementation chosen for the classification model. The Keras library predicts the negative class if the score and threshold are equal, but other tools or frameworks may handle the case differently. Says they predict a negative class if the score and threshold are equal. Oh, okay. So for the Keras library, they stick to using it's super powerful for ML developers. I see. Okay, cool. We'll come back to it to see what they have. But yeah, so what we're learning is that this library, they predict for as long as the probability is equal to the threshold probability, it is deemed as negative. Okay. Suppose the model scores one email as 0.99, predicting that that email has a 99% chance of being spam, and another email as 0.51, predicting it has a 51% chance of being spam. If you set a classification threshold to 0.5, the model will classify both emails as spam. If you set a threshold to 0.95, only the email scoring 0.99 will be classified as spam. That makes sense. While 0.5 might seem like an intuitive threshold, it's not a good idea if the cost of one type of wrong classification is greater than the other, or if the classes are imbalanced. It's not a good idea if the cost of one type of wrong classification, is greater than the other, or if the classes are imbalanced. If only 0.01% of emails are spam, or if misfiling legitimate emails is worse than letting spam into the inbox, labeling anything the model considers at least 50% likely to be spam as spam produces undesirable results. Okay, that's true. Confusion matrix. The probability score is not reality or ground truth. There are 4 possible outcomes for each output from a binary classification. For the spam classifier example, if you let out the ground truth as columns and the model's prediction as rows, the following table called a confusion matrix is the result. Okay, so we have the actual positive, actual negative, predictor positive, predictor negative. Oh, this is what they meant. So when they said the top left, in fact, like I thought you said graph, the curve. Oh my goodness! Like I was imagining a graph. So at a point, I was wondering which type of graph this could be. Okay, so it's just a matrix. The top left is true positive. This is a spam email correctly classified as a spam email. These are the spam messages automatically sent to the spam folder. Then actual negative are the false positives. No, so actual negative and predicted positive. The false positive, that's a not spam email misclassified as spam. These are the legitimate emails that wind up in the spam folder. Then we have the predicted negative, that's false negative, a spam email misclassified as not spam. These are spam emails that aren't caught by the spam filter and make their way into the inbox. So that's false negative. So a spam email misclassified as not spam. Then for true negative is a not spam email correctly classified as not spam. These are the legitimate emails that are sent directly to the inbox. Okay, I think I have a good idea of what the confusion matrix is right now. Just the matrix to show when our actual value meets the predicted value, or if our actual value doesn't correspond to the predicted value in terms of the classes we are putting it in. Notice that the total in each row gives all predicted positives, the TB plus. Okay, predicted positive, and all predicted negatives, regardless of validity. The total in each column, so it was talking about row, predicted positive. The total in each column is meanwhile gives all real positives and all real negatives, regardless of model classification. When the total of actual positives is not close to the total of actual negatives, the data set is imbalanced. Okay. When the total of actual positives is not close to the total of actual negatives, the data is imbalanced. An instance of an imbalanced data set might be a set of thousands of photos of clouds where the rare cloud type you are interested in, say volutus clouds, only appears a few times. In fact, I have no idea what. In fact, I didn't even know like there are different types of clouds. Different types of clouds. All right. Then the effective threshold on true and false positives and negatives. Different thresholds usually result in different numbers of true and false positives and true and false negatives. The following video explains why this is the case. Sorry. Oops. Just got a call. Okay, let me put it there if the call comes through again. Imagine a phishing or malware classification model where phishing and malware websites are in the class labeled true for one, and harmless websites are in the class labeled 0 for false. So if it looks like a phishing site, that is 1. If it is a safe site, that is 0. Okay. This model mistakenly classifies a legitimate website as malware. What is this called? So this is a false positive. This model mistakenly classifies a legitimate website as malware. The classification as malware is a positive. So this is a false positive. A negative example has been wrongly classified as positive. Okay. In general, what happens to the number of false positives when the classification threshold increases? When classification threshold increases, the number of false positive is going to decrease. False positives will decrease and true positives is likely to increase. No! Using the slider above, try setting the threshold to 0.1 and dragging it to 0. Threshold to 0.1. So at 0.1, true positive is 51. That is when the threshold is decreased, true positive increases. Oh, increases. And the false positives here, false positive is 39. But when we increase this, false positive would decrease and true positive is also decreasing. Interesting. So it's decrease. Both decrease. Oh, interesting. So in this case, both will decrease. As the threshold increases, the model will likely predict fewer positives overall, both true and false. A spam classifier with a threshold of 0.9999 will only label an email as spam if it considers the classification to be at least 99.99% likely, which means it's highly unlikely to mislabel a legitimate email, but also likely to miss actual spam email. Next up. In general, what happens to the number of false negatives when the classification threshold increases? Number of false negatives. So let's think about it. False negatives when classification threshold increases. So as you increase the threshold, false negatives will decrease. Because ideally, if it was coming in here, you increase the, it will increase. Yeah. False negatives will increase. Let's go back. As we increase this, the number of false negatives, let's say, false negatives is 46. So ideally it would increase because you're allowing more to be in the negative. So whatever you allow more of, so here false negative would increase, true negative will also increase. Okay. And what about true negative? Both will increase. As the threshold increases, the model will likely predict more negatives overall, both true and false. And at a very high threshold, almost all emails, both spam and not spam, will be classified as not spam. Okay. Right. So at least I've gotten the concept of classification. We've also gotten confusion matrix and false positives, the false negatives, true positive, true negatives. Good. Next thing is accuracy, recall, precision, and related metrics. So I guess we're trying to evaluate our classification model. True and false positives and negatives are used to calculate several useful metrics for evaluating models. Which evaluating metrics are most meaningful depends on the specific model and the specific task, the cost of different misclassifications, and whether the dataset is balanced or imbalanced. All of the metrics in this section are calculated at a single fixed threshold. All of the metrics in this section are calculated at a single fixed threshold and change when the threshold changes. Very often, the user tunes the threshold to optimize one of these metrics. Okay. All the metrics in this section are calculated as at a single fixed threshold. Okay, so you use one threshold, then you calculate all the metrics. Then you change when the threshold changes. So, yep, you change all those metrics when the threshold changes. So we set one threshold and we calculate all the metrics. Very often, the user tunes the threshold to optimize one of these metrics. Okay. You tune the threshold to optimize them. So these are the metrics that tells us about the performance of the model. So if we are not very happy with any one of them, then we may want to tune the threshold to optimize that metric. Okay, cool, understood. Accuracy. Let's think about it. How accurate a model is. I would think that it would have to do with the percentage of true positives and true negatives, right? Like if it says that this is positive, then it should be positive. And if it says this is negative, then it should be negative. Anyway, I'm curious. Accuracy is the proportion of all classification that were correct, whether positive or negative. Yeah, I got it. It is mathematically defined as correct classification over total classification. So accuracy is equal to correct classification over total classification. So this is equal to true positive plus true negative all over true positive plus false positive plus true negative plus false negative. Okay. In a spam classification example, accuracy measures a fraction of all emails correctly classified. All emails correctly classified. So that tells us how accurate the model is. So when we are talking about model accuracy in classification, we're thinking about what the model got correct. So we don't focus on what it got wrong. Accuracy is more what it got correct. So the true positives and the true negatives over the total classification. Okay. A perfect model would have 0 false positives and 0 false negatives, and therefore an accuracy of 1 or 100%. Yeah. Because it incorporates all 4 outcomes from the confusion matrix. Given a balanced data set with similar numbers of examples in both classes, accuracy can serve as a coarse-grained measure of model quality. For this reason, it is often the default evaluation metric for generic or unspecified models carrying out generic or unspecified tasks. However, when the data set is imbalanced or where one kind of mistake, the false negative or false positive, is more costly than the other, which is the case in most real-world applications, it's better to optimize for one of the other metrics instead. For heavily imbalanced data sets, where one class appears very rarely, say 1% of the time, a model that predicts negative 100% of the time would score 99% of accuracy despite being useless. Wait. For heavily imbalanced data sets where one class appears very rarely, say, oh, that class appears only 1% of the time, a model that predicts negative 100%, because it's so small, it could actually predict the 100%, but then would score 99% on accuracy, but despite being useless. Yeah, makes sense. In machine learning, words like recall, precision, and accuracy have mathematical definitions that may differ from or be more specific than more commonly used meanings of the word. Okay, at least now we know accuracy. Accuracy is the total that we got correct over the total of classification that was done. And the total that we got correct is the true positives and the true negatives. Recall or true positive rate. So recall is also known as true positive rate. That's a rate of true positives. The rate of true positives. Interesting. Recall is also known as true positive rate. What percentage of the positive classification was true? No. Correctly classified actual positive of all actual positives. Yeah. But wait, all actual positives is true positive plus false negative? All actual positive. Oh, false negative means that it considered it to be negative, but it's actually true. Okay. So the actual one that it got, which is the true positive, is the numerator divided by the true positive plus the false negative, which means the things that were true, but it classified it as being false. Okay, the opposite. TP over TP plus FN. The true positive rate. So accuracy was the rate of being correct, like accurate. So it was true positive, true negatives, all divided by all classification. And then the recall. So recall is recall, ability to recall. So ability to remember. But it's talking about the true positive rate. So recall is true positive rate. So we only focus on the things that it got. Not just correct, but the ones that it predicted to be true as against the total true that we have in the data set. Okay. So false negatives are actual positives that were misclassified as negatives, which is why they appear in the denominator. In the spam classification example, recall measures the fraction of spam emails that were correctly classified as spam. This is why another name for recall is probability of detection. So another name, probability of detection. Probability of detection. Probability of detection. Recall. So in the spam classification example, recall measures the fraction of spam emails that were correctly classified as spam. Fraction of, so the total of spam, how many of them did we correctly get as spam? That is recall. This is why another name for recall is probability of detection. So what's the probability that you detect me, right? Because if I'm spam, what's the probability that you detect me? It's the number that you detected over the total spam. It answers the question, what fraction of spam emails are detected by this model? Okay. A hypothetical perfect model would have 0 false negatives and therefore recall of 1, which is say 100% detection rate. In an imbalanced data set where the number of actual positives is very low, recall is a more meaningful metric than accuracy. because it measures the ability of the model to correctly identify all positive instances. So where the actual positives is very low, the focus here would be just the positive one. So no matter how low it is, if you can get those ones correct, or the percentage of detecting those small number of positives is high, then it means it has high recall. For applications like disease prediction, correctly identifying the positive cases is crucial. A false negative typically has more serious consequences than a false positive. False negative, so the person may end up dying without knowing because you misdiagnosed. When they had the condition and you told them they didn't have the condition, then you're going to die out of it. But let's say if they had a false positive is say, oh, the person has a condition when they don't have. So that one, if the medication you give them is not deadly, then they could potentially survive long after, right? Okay, makes sense. Recall. A false negative typically has more serious consequences than a false positive. For a concrete example, comparing recall and accuracy metrics, see the notes in the definition of recall. Okay. False positive rate. So recall was true positive rate. And now let's talk about false positive rate. This is like the rate false positive. So false positive rate. This is whatever. So the total of things that were supposed to be negative. No. The proportion of all actual negatives that were classified incorrectly as positive. False positive rate. So whatever was classified as false positive means that it's actually a negative, and we said it's a positive. So what is the total negative? Out of the total negative, how many of these did we wrongly identify? Okay. That's false positive rate. False positive rate. Which is why, wait, okay, is the proportion of all actual negatives that were classified incorrectly as positives, also known as the probability of false alarm. The other one was called probability of detection. This is probability of false alarm. Probability of false alarm. Interestingly, I'm beginning to feel sleepy. Oh man. Okay. A perfect model. All right. The formula is incorrectly classified as false positive over all actual negatives. False positive plus true negatives. Beginning to feel sleepy. False positives are actual negatives that were misclassified, which is why they appear in the denominator. In a spam classification example, false positive rate measures the fraction of legitimate emails that were incorrectly classified as spam, or the model's rate of false alarms. A perfect model would have zero false positives and therefore FPR of 0.0, which is to say 0% false alarm rate. For an imbalanced data set, false positive rate is generally a more informative metric than accuracy. However, if the number of actual negatives is very low, false positive may not be an ideal choice due to its volatility. If the number of actual negatives is very low. So one, how many of them will we detect as false positive? We want that rate. But then if it is very low, then we might not get the false positives because it's really low. Okay. For example, if there are only 4 actual negatives in a data set, one misclassification results in an FPR of 25%, while a second misclassification causes it to jump to 50%. In cases like this, precision describedness may be a more stable metric for evaluating the effects of positives. Okay, so I understand the concepts. I think what would be challenging is if they gave me that these scenarios and say in an imbalanced data set where this is that, which of these? So I need to reflect on them and see if I can remember. Because I don't want to be memorizing these things. Okay, but at least I understand what false positive rate is. Now let's look at precision. Precision is a proportion of all the model's positive classifications that are actually positive. Wait, in accuracy, we talked about the correct classification over total classification. So true positive versus true negatives over all classification. In precision, we are talking about proportion of all the model's positive classification. So positive classification, that's true positive and false positive. The proportion of all the positive classifications that are actually positive. So true positive plus false positive is the denominator. Okay. Then true positive numerator. Okay. Ooh, slightly different from the recall. Slightly. Precision. So what percentage of the things that we identified as positive is actually positive, right? What percentage of what we classify as positive is truly positive? Okay. And precision, so that is TP over TP plus FP. In a spam classification example, precision measures the fraction of emails classified as spam that were actually spam. A hypothetical perfect model would have 0 false positives and therefore a precision of 1. In an imbalanced data set where the number of actual positives is very, very low, say 1 to 2 examples in total, precision is less meaningful and less useful as a metric. Precision improves as false positive decreases. Okay. While recall improves when false negatives decreases. So precision is more on false positive, but recall is on false negatives. Go. But as seen in the previous section, increasing the classification threshold tends to decrease the number of false positives and increase the number of false negatives, while decreasing the threshold has the opposite effect. As a result, precision and recall often show an inverse relationship. Okay. Precision and recall have an inverse relationship. Right. Precision and recall have an inverse relationship where improving one of them worsens the other. Improving precision worsens recall. I'll have to take my time to come and look at this, but at least I've learned about classification, I've learned about confusion matrix, and I've learned about some of the metrics that we use to evaluate a classification model. So we've talked about accuracy, recall, false positive rate, and precision. Those are the four that we've talked about. So the next thing that I'm going to learn is when do you choose what? And from the examples that we're given, either imbalances between in the data, then depending on the kind of imbalance, some of the metrics would be more important than others. So I need to be able to understand that. And because I do not like to memorize things, I have to find a way that makes this stick. Okay. And I'll continue later. ROC and AUC, prediction bias, multi-class classification. I think one of the things that I should start doing as well is now getting into doing the actual classification, because this has given me an idea of what a classification is, but do we use the same calculations as we do with the logistic regression model, or is there something else? Like, are we using the sigmoid function? Like, all of those things that we learned in regression, is it the same thing we have to use in classification? I need to look into that and also find some data sets that I can classify and build a classification model to test that. Okay, so I will try and do more live stream. And just for the record, currently, if I'm learning anything, it's probably machine learning. I'm also learning to speak French. Yeah, so if you come across this and you're good at French, come and help me. I'm learning to speak French. I'm learning mastering more of the AI engineering bit as well. So playing with various AI agents and testing them, and also building AI agents. And probably I might do live streams where I build things too. I'm thinking about it, but I might do live streams. I enjoy building stuff, especially now that AI makes building so easy and fun. I am building a lot of things, and maybe I'll stream myself building some of these. Okay, I'll catch you in the next stream. For now, I don't really have a schedule. For instance, I'm going to get some sleep right now. And if I wake up and I still have some energy to continue learning, I might as well do a stream. So, see you when I see you. Until then, bye for now.